Time is woven into every aspect of human experience, yet its nature is far stranger than the constant ticking of clocks might suggest. From the moment we wake to the moment we sleep, we perceive time as a continuous flow, a river carrying us from the past into the future, unidirectional and inevitable. We remember the past as a fixed landscape of events, and we anticipate the future as an open horizon yet to be shaped. Our minds create a seamless continuity, even though the raw signals arriving from our senses are discrete and fragmented. Neuroscientists have revealed that the brain stitches together events, separated by milliseconds, into coherent moments that we experience as flowing time. This process, known as temporal integration, is the reason why a flickering sequence of images appears as smooth motion, why a melody emerges from individual notes, and why we can anticipate the beat of our own footsteps. It is not the universe that demands this flow, but our brains that construct it for survival and coherence. The perception of past, present, and future is deeply rooted in memory. Without the ability to store past experiences and compare them with new sensations, the notion of duration would evaporate. Memory encodes change, and change is what our minds interpret as the passage of time. Attention and emotion further modulate this sense, stretching moments of fear into what feels like eternity, and compressing periods of routine into fleeting instants. Our psychological experience of time is malleable, dependent on context and internal states, yet we project this internal construct outward as if it were a property of the cosmos itself. The apparent flow of time, vivid and unyielding to us, is in part a reflection of how our brains organize reality rather than a fundamental feature of the universe. Humanity has long sought to measure and control this elusive dimension. Ancient civilizations tracked the sun and the stars, inventing sundials and water clocks to partition the day. Mechanical clocks, with gears and pendulums, emerged in medieval Europe and began to standardize the passage of hours and minutes. But even they were subject to mechanical imperfections. It was not until the development of atomic clocks in the 20th century that humanity achieved an unprecedented precision in timekeeping, measuring intervals to billionths of a second. Yet even these instruments do not define time itself. They merely provide a consistent framework to quantify changes and sequence events. Time, in this sense, is operational. Physicists measure it by observing motion, the vibration of atoms, or the decay of unstable particles. The tick of a clock is not a manifestation of the flow of time, but a record of periodic changes occurring within the universe. Physics approaches time not as a river, but as a coordinate, much like the spatial dimensions that define the positions of objects. In classical Newtonian physics, time is absolute, flowing uniformly and independently of the observer. It is the backdrop against which motion and causality unfold, a silent stage on which the theater of the universe is performed. This conception aligns with everyday intuition, but it begins to falter under the scrutiny of modern physics. Einstein's theories of relativity revealed that time is not universal and fixed. Instead, it is intimately linked with space and influenced by motion and gravity. The once sacrosanct division between past, present, and future dissolves when velocities approach the speed of light, or when massive objects warp spacetime. Clocks moving at different speeds or situated in different gravitational potentials measure time differently, a phenomenon confirmed repeatedly by experiments involving atomic clocks flown in airplanes and satellites orbiting Earth. Time is no longer a uniform river, but a malleable dimension, entwined with space in a four-dimensional fabric called spacetime. Even the notion of simultaneity is called into question. Events that appear simultaneous to one observer may occur at different moments for another moving relative to the first. The idea of a universal now is an illusion born of our limited perspective. Minkowski, one of Einstein's collaborators, formalized this view by treating space and time as inseparable, forming a geometric entity where all events exist within a single structure. In this framework, time does not flow in the traditional sense. Instead, all points in space-time coexist, and the experience of movement from past to future is a product of our consciousness navigating this structure. The brain, in its relentless drive to perceive change and continuity, interprets this geometric reality as a river of moments, giving rise to the human illusion of flowing time. If time is woven into the very fabric of the universe as a dimension rather than a force or substance, then our experience of its passage is a construct, an emergent phenomenon generated by neural processes. The clocks we build, the schedules we maintain, and the calendars that mark our lives serve as proxies for this emergent experience, not windows into a flowing entity. The distinction between operational time and perceived time becomes crucial as we venture into physics at extreme scales. In the depths of space and near massive objects, time behaves differently. Seconds stretch or shrink depending on relative motion and gravitational influence, yet our minds remain tethered to a psychological now. We are creatures bound by perception, projecting continuity onto a universe where the past, present, and future may all exist simultaneously, waiting to be observed and interpreted. The journey to understand the true nature of time requires abandoning the comforting notion of flow and confronting a reality where the human experience is just one perspective among many. If time does not flow as we feel it, then what is it? Is it a backdrop, a coordinate, an emergent phenomenon, or an illusion of consciousness? To answer this, we must look beyond intuition and into the revolutionary insights of physics that reshaped our understanding of reality itself, beginning with the work of one man whose vision of the cosmos forever intertwined time with space. Time as a dimension reveals itself most clearly when we consider the insights of Einstein. In 1905, he proposed that simultaneity is not absolute, that two observers moving relative to each other can disagree about the order of events. This radical idea, now known as special relativity, demonstrated that time is intertwined with motion. A clock moving rapidly relative to an observer ticks more slowly than one at rest, a phenomenon called time dilation. Experimental confirmations are abundant. Particles known as muons, created by cosmic rays in the upper atmosphere, decay more slowly as they race toward Earth, reaching the surface in numbers that would be impossible if time were uniform. Atomic clocks flown on airplanes register measurable differences from their counterparts on the ground. Even the satellites of the Global Positioning System must account for these relativistic effects, or their navigational calculations would quickly drift into error. Time is no longer universal, and the river of experience is revealed as a flexible framework shaped by velocity and gravity. Einstein extended these principles in 1915 with general relativity, showing that gravity is not a force acting at a distance, but a curvature of space-time itself. Massive objects bend the four-dimensional fabric, and this bending affects the passage of time. A clock near the surface of Earth runs slightly slower than one in orbit, a fact accounted for daily in satellite communications. Near a black hole, this effect is magnified. The immense gravity warps time so severely that an observer hovering near the event horizon would experience seconds, while distant observers see years pass. Space and time are no longer separate entities, but aspects of a geometric reality, where matter tells spacetime how to curve, and curved spacetime tells matter how to move. The familiar past, present, and future dissolve into a single continuum in which all events coexist from a four-dimensional perspective, a construct that challenges intuition and demands new ways of thinking about reality. Minkowski formalized this geometric vision by representing spacetime as a four-dimensional manifold in which the coordinates of space and time are inseparable. Distances between events are measured not merely in meters or seconds, but in space-time intervals, combining both spatial and temporal separations. This mathematical framework allowed physicists to predict phenomena with remarkable accuracy and provided a conceptual foundation for the block universe interpretation. According to this view, every event past, present, and future exists within the space-time manifold. Our perception of a moving now is a product of consciousness navigating this structure. The universe, in this sense, is a static four-dimensional landscape, yet the mind experiences it as dynamic, flowing, and continuous. The continuity we feel is an emergent property of cognitive processes, not a fundamental feature of reality. Experimental confirmations of these ideas continue to deepen our understanding. Gravitational redshift, observed in photons climbing out of Earth's gravitational well, illustrates that time itself is affected by gravity. The Hafele and Keating experiment of 1971, which involved flying atomic clocks around the world on commercial airliners, demonstrated measurable differences in elapsed time, confirming relativistic predictions. Even at the scale of our solar system, the motion of planets and the synchronization of clocks reveal that time is malleable and intimately connected with space. The implications extend beyond mere physics. They challenge our notions of causality and the linear progression of events. The The past may not be fixed in the way we assume, nor the future predetermined, but both exist within the geometric framework of spacetime. Our experience of moments flowing from one to another is a cognitive projection, a narrative created by the brain to navigate this intricate structure. The block universe presents a philosophical puzzle. If all moments exist simultaneously, why do we feel time passing? Why does memory reach backward and anticipation forward? The answer lies in entropy and the arrow of time. While the geometric structure of spacetime is symmetric, physical processes are not. The second law of thermodynamics dictates that entropy increases, providing a direction to change. The early universe began in a state of remarkably low entropy, as evidenced by the uniformity of the cosmic microwave background. From that initial condition, systems evolved toward higher entropy, generating the psychological sense of past and future. Memory itself is an entropic process, recording states and enabling the brain to reconstruct sequences of events. Even in a four-dimensional spacetime where all events exist, the unfolding of entropy creates the subjective impression of flow. Time, as experienced, emerges from the combination of geometric structure and physical asymmetry. Our daily lives are guided by this emergent perception. Clocks, schedules, and plans impose an external order on the sequences of events, yet they reflect an internal experience that arises from neural computation and thermodynamic directionality. The illusion of a moving now persists because the mind integrates information over time, anticipates future events, and recalls the past in a coherent narrative. This narrative is powerful, shaping decision-making, emotion, and culture. Stories, music, and art are all structured around the progression of events, reflecting a temporal framework deeply embedded in human consciousness. Yet beneath this familiar experience lies a universe indifferent to the flow, a cosmos in which time is a dimension, not a river, and in which every moment is already situated in the fabric of space-time. As we contemplate these ideas, it becomes clear that our perception of time is a construct, a way for consciousness to interact with a four-dimensional reality. The clocks that govern our lives are tools to measure changes, not arbiters of an independent flow. The past, present, and future exist as coordinates within a geometric manifold, and the brain interprets sequences of events to create the sensation of passage. This understanding challenges deeply held intuitions, suggesting that the flow of time is not a property of the universe, but an emergent feature of perception. It also sets the stage for exploring deeper questions. If time is a dimension, what governs its origin, its direction, and its fate? To answer these questions, we must venture further into physics, beyond human intuition and everyday experience, into the realms of relativity, entropy, and quantum mechanics, where the true nature of time begins to reveal itself. As we peer deeper into the nature of time, the distinction between perception and physical reality becomes ever clearer. Human experience treats moments as fleeting, yet physics suggests they coexist within a vast, four-dimensional structure. Memory, anticipation, and attention craft a narrative of flowing time. Yet this is a story authored by the brain rather than the universe itself. Neural mechanisms integrate sensory input, creating a coherent timeline from events that are fundamentally discrete. Milliseconds are stitched together into seconds, seconds into minutes, and minutes into hours, generating the seamless experience we call the present. Attention accelerates or decelerates this perceived pace, making moments of fear or excitement feel prolonged while monotonous stretches collapse into brevity. Emotion imbues temporal experience with richness, coloring duration with subjective weight. Even the perception of causality emerges from this construction, giving order and meaning to sequences of events within the mind. Without the machinery of consciousness, the river of time would evaporate, leaving only the static coordinates of space-time, indifferent and eternal. The invention of clocks is humanity's attempt to impose an objective framework on this subjective experience. Sundials, water clocks, and mechanical devices segmented the day, allowing coordinated activity across communities. Yet these instruments were always measuring motion or periodic processes, never time itself. The development of atomic clocks marked a leap in precision, allowing measurement of intervals so exact that a second could be defined by the vibrations of cesium atoms. Even then, These measurements do not capture the essence of time. They provide a method to quantify change and sequence events, reflecting operational time rather than an intrinsic flow. Physicists define a second by counting oscillations, a process rooted in the behavior of matter rather than a passage experienced by consciousness. Time, as measured scientifically, is relational. It is a metric to compare events, a coordinate within spacetime, and a tool for prediction. The flow that we feel is an emergent property, arising from neural computation and statistical mechanics. Einstein's insight redefined these concepts. Time is not absolute but relative, affected by velocity and gravity. Special relativity reveals that moving clocks run slower, and simultaneity is observer-dependent. General relativity shows that gravity curves spacetime, slowing time near massive objects. Black holes exemplify this distortion. An observer near the event horizon would experience moments, while the universe outside ages by centuries. These predictions are not theoretical musings, but have been repeatedly confirmed through observations of muon decay, atomic clocks in motion, and the precise operation of satellites. Time is thus a dimension, a coordinate integrated with space, forming a unified geometric fabric that hosts all events. Our minds perceive a moving present, yet this is a navigation of the landscape, not the landscape itself. The block universe interpretation, which treats all events as equally real within spacetime, follows naturally from this framework. Past, present, and future coexist in a four-dimensional manifold, with our consciousness tracing a path through these coordinates. Yet the experience of temporal flow is reinforced by the asymmetry of physical processes. Entropy provides the arrow of time, guiding change in a preferred direction. The early universe began in an extraordinarily low entropy state, as revealed by the cosmic microwave background. Systems evolve toward higher entropy, producing irreversible processes that the brain interprets as the passage of time. Memory formation itself depends on this increase, recording states of the world and enabling prediction. Even in a universe where all events exist, the unfolding of entropy imparts the sensation of before and after. Time, as experienced by humans, emerges from the intersection of geometric structure and physical asymmetry. Consciousness perceives a trajectory, yet the underlying manifold contains all points. The subjective now is a result of neural integration over temporal windows, attention to sensory inputs, and encoding of sequential memories. Reality, in contrast, is indifferent to this perception, existing as a coherent structure of events, independent of observation. This understanding reshapes our conception of life and experience. Every choice, every memory, every anticipation exists within a framework that does not rely on flow. The brain interprets sequences to navigate the world effectively, yet the universe itself operates according to coordinates, metrics, and invariants. The clocks, calendars, and schedules we depend upon are extensions of this cognitive architecture, tools to manage events and coordinate actions. Our perception of time is powerful, shaping art, music, and narrative, but it is ultimately an emergent phenomenon superimposed on a static and geometric reality. Recognizing this distinction does not diminish experience but deepens it, revealing the profound interplay between human consciousness and the fabric of spacetime. We inhabit a world in which every instant is situated, yet our minds trace paths through it, creating the sensation of flow, movement, and progression. As this chapter closes, the stage is set to explore how this understanding expands with relativity. If time is a dimension rather than a river, then motion, gravity, and the structure of the cosmos reveal its malleable and interconnected nature. The human illusion of time prepares us for a journey into the very geometry of reality, where past, present, and future coexist, and where clocks and consciousness alike are guides to navigate a universe that defies intuition. Understanding time as a dimension opens new questions. How does it interact with space, matter, and energy? What governs its direction and origin? How does perception reconcile with physics? The answers lie in the revolutionary insights of Einstein, Minkowski, and the experiments that confirm a universe more astonishing and intricate than our senses ever imagined. In embracing the human illusion, we glimpse the deeper truth, a cosmos where time is written into the structure of existence, waiting to be explored beyond the horizon of intuition. The world of physics before 1905 was dominated by Newtonian certainty. Time was absolute, a uniform river flowing independently of matter and motion. Seconds ticked the same for all observers, and the universe marched to a single unyielding clock. Space and time were separate, immutable, and universally agreed upon. This framework explained planetary motion, terrestrial mechanics, and much of everyday experience with remarkable accuracy. Yet it could not reconcile the behavior of light with the laws of mechanics. Experiments in the late 19th century, most famously the Michelson and Morley experiment, demonstrated that the speed of light is constant in all reference frames, contradicting expectations if time were absolute. The stage was set for a revolution, one that would redefine not just physics, but our very understanding of reality. Albert Einstein proposed that the laws of physics are the same for all observers in uniform motion, and that the speed of light is invariant, forming the foundation of special relativity. This simple principle led to consequences that defy everyday intuition. Time, he showed, is relative. Two observers moving at different velocities will measure different intervals between the same events. Clocks in motion run slower relative to stationary clocks. Lengths contract along the direction of motion, and mass increases with velocity. The faster one travels, the more pronounced these effects becoming extreme as speeds approach that of light. This was not speculative. Predictions could be tested. Subatomic particles moving at nearly light speed persist longer than expected. Airplanes carrying atomic clocks show measurable time differences, and GPS satellites must constantly adjust for relativistic effects to provide accurate positioning. The constancy of the speed of light and the relativity of time shattered the classical concept of a universal now, demonstrating that time is not an independent river, but a dimension intertwined with space. In 1915, Einstein extended these ideas to include gravity, producing the theory of general relativity. Gravity was no longer a force acting at a distance, but a manifestation of the curvature of spacetime caused by mass and energy. Objects follow the straightest possible paths in curved spacetime, and the presence of matter affects both the geometry and the passage of time. A clock near a massive object ticks more slowly than one further away, a phenomenon known as gravitational time dilation. Light is bent by massive bodies, as confirmed during solar eclipses, when starlight, passing near the sun, was observed to shift, matching Einstein's predictions. This profound insight united space and time into a four-dimensional continuum, revealing a cosmos in which geometry dictates the motion of matter and the experience of time itself. The distinction between space and time dissolves, replaced by the concept of spacetime, where every event is a coordinate, and the flow of time is observer-dependent. Hermann Minkowski formalized this union, describing spacetime as a four-dimensional manifold, with time as the fourth coordinate. Distances between events are measured not by spatial separation alone, but by spacetime intervals, combining temporal and spatial differences into a single invariant. This mathematical structure elegantly explains relativistic phenomena and provides a conceptual foundation for the block universe interpretation. Within this framework, past, present, and future coexist, and the notion of a universal present becomes untenable. Each observer experiences a unique slicing of spacetime, creating a personal sequence of events while remaining consistent with the geometric structure. The world is no longer a stage on which events unfold in a single timeline. It is a landscape of possibilities, with consciousness navigating paths within this four-dimensional terrain. Experimental evidence confirms these insights. The decay of muons, generated by cosmic rays, illustrates time dilation, as they survive longer when moving at high velocities than if time were absolute. The Hafei and Keating experiment of 1971 flew atomic clocks around the Earth, revealing that clocks in motion differ measurably from stationary counterparts. Gravitational redshift demonstrates that light climbing out of a gravitational well loses energy, reflecting the slowing of time in stronger gravitational fields. GPS satellites orbiting Earth constantly adjust for both relative motion and gravitational effects to maintain accuracy, providing everyday confirmation of relativistic predictions. These experiments are not curiosities, they are essential for technology and navigation, demonstrating that time is malleable and intimately connected with space and motion. The implications of relativity extend beyond physics into the philosophical realm. If time is not universal, the past and future may exist in a four-dimensional manifold, challenging the notion of a flowing present. Free will and causality remain intact, but they are reframed. Events occur within space-time coordinates, and while the brain experiences sequences, the underlying structure is geometric and static. Time does not move, consciousness moves through it. This shift in perspective requires abandoning intuition and embracing a view in which all events coexist, waiting to be experienced from different vantage points. The observer becomes central, for time is not an external absolute, but a relational property that depends on motion, gravity, and the path taken through space-time. Relativity also redefines simultaneity, one of the most intuitive yet misleading concepts of classical physics. Two events that appear simultaneous to one observer may occur at different times for another moving relative to the first. There is no universal now. The division between past, present, and future is observer-dependent, a product of perspective rather than an inherent property of the cosmos. This insight dissolves the comforting linearity of time, replacing it with a complex structure in which coordinates, intervals, and geometry determine experience. Our perception of a flowing present is a cognitive construct superimposed upon a static, four-dimensional reality. Understanding this prepares us to explore deeper consequences, including the concept of the block universe, entropy, and the directionality of time, all of which emerge naturally from Einstein's revolutionary insights. Relativity transforms not only the measurement of time, but also the very geometry of the cosmos. Minkowski's formulation presents space-time as a unified arena where events are coordinates rather than points along a flowing river. The intervals between events, called space-time intervals, remain invariant for all observers, providing a consistent framework, despite differences in perceived time or distance. In this structure, what one observer experiences as a single moment may appear stretched or compressed to another moving relative to the first. This relativity of simultaneity is not a flaw but a fundamental property of nature, demonstrating that our intuitions about absolute time are limited to low-speed, weak gravity conditions familiar on Earth. The universe at large, from the dance of planets to the behavior of light near massive stars, obeys a different order, one dictated by the geometry of space-time itself. Experimental confirmation of these predictions is robust. Gravitational time dilation has been verified through the Pound-Rebka experiment, which measured the redshift of gamma rays moving in Earth's gravitational field. The effect, though tiny, matches theoretical calculations precisely. Atomic clocks flown on airplanes and rockets demonstrate that motion and altitude affect elapsed time as predicted by special and general relativity. Even technological systems we rely upon daily, such as GPS, require constant adjustment for these relativistic effects. Without accounting for time, dilation, and gravitational slowing, navigational errors would accumulate at several kilometers per day. These examples demonstrate that time is not an immutable background, but a dynamic dimension shaped by motion and mass. The perception of a universal clock is convenient for human life, but does not reflect the underlying physical reality. The philosophical implications are profound. If time varies with motion and gravity, then the notion of a universal past and future collapses. The block universe interpretation follows naturally from these principles. In a four-dimensional space-time, all events exist simultaneously, their coordinates fixed within the geometric manifold. The experience of a flowing present is an artifact of consciousness moving along a trajectory through this structure. Past, present, and future are not ontologically distinct. They are relative labels, applied by observers navigating space-time. This interpretation preserves causality while challenging linear intuition. Free will is experienced sequentially, yet, in the block universe, the sequence is a path through existing coordinates, rather than the creation of new moments. The universe, in this view, is timeless in its structure, and the flow of time emerges from the perspective of conscious observers. One of the most dramatic illustrations of relativistic time occurs near massive objects such as black holes. The immense gravity warps space-time so that clocks slow dramatically as they approach the event horizon. For a distant observer, a person falling toward the black hole appears to freeze at the edge, the seconds stretching toward infinity, while, from the perspective of the falling observer, time proceeds normally. Light and information from near the event horizon are increasingly redshifted, revealing how gravity and geometry dictate the passage of time. These effects are not science fiction. They follow directly from Einstein's equations and have been observed in astrophysical contexts. Gravitational lensing, the bending of light by massive bodies, confirms the curvature of space-time and the interdependence of space and time. The universe is a four-dimensional fabric in which mass, energy, and motion together shape the rhythm of events. Even within the solar system, time is malleable. Mercury's orbit exhibits a precession that cannot be accounted for by Newtonian physics alone. General relativity provides the precise correction, explaining the discrepancy observed in the 19th century. Satellites in orbit experience both velocity-based time dilation and gravitational time dilation, and these effects must be corrected to maintain synchronization. Experimental tests on Earth using highly accurate atomic clocks confirm that altitude and motion affect elapsed time as predicted. The practical and philosophical consequences intertwine. We rely on time as a tool, yet its behavior defies intuition, revealing the malleable, relational, and geometric nature of the dimension we call time. Relativity also reframes the concept of simultaneity in ways that challenge everyday understanding. Consider two events occurring in different locations. Observers in relative motion will disagree about which event occurs first. There is no universal clock to dictate a single sequence. Each observer constructs their own timeline based on position and velocity. This relativity emphasizes that our perception of a linear past, present, and future is not a property of the cosmos, but a feature of consciousness navigating space-time. Physics replaces the absolute now with a network of interconnected events, whose order depends on the observer's trajectory. Time becomes a coordinate, not a river, and the experience of its flow emerges from the interplay between geometry and perception. These insights prepare the mind for the concept of the block universe. If all events exist as coordinates within space-time, then what we call the past and future are simply labels for positions along an observer's path. Consciousness traces a trajectory through this manifold, experiencing moments sequentially, even though they coexist. Entropy and thermodynamics provide the arrow that guides our perception of direction, reinforcing the subjective sense of flow. Our cognitive architecture interprets sequences, anticipates consequences, and records memory, creating the vivid experience of time passing. Yet the universe itself contains all events, organized geometrically and independently of observation. The stage is set to explore how the block universe emerges naturally from relativity, how the arrow of time reconciles perception with physical law, and how the human experience of time is woven into this geometric tapestry. The block universe concept arises naturally from Einstein's relativistic insights. In a four-dimensional space-time, every event is a coordinate, fixed within the geometric structure, existing independently of observation. Past, present, and future coexist, and what we perceive as the flow of time is a traversal of consciousness through this manifold. The river of seconds we feel is the mind interpreting sequences, constructing narratives, and integrating memories to navigate an otherwise static cosmos. This perspective reconciles the relativity of simultaneity with everyday experience, showing that subjective time and physical time are distinct yet interdependent. Conscious beings experience a dynamic unfolding while the universe itself remains a coherent, timeless structure. Experimental confirmations of the block universe framework abound. Time dilation effects are visible not only in high-energy particle experiments, but also in astronomical phenomena. Light from distant stars and galaxies exhibits gravitational redshift, reflecting the influence of mass on space-time curvature and the corresponding slowing of time. The precision required for satellite navigation further demonstrates that time is not uniform. Every clock in motion, or affected by gravity, measures its own interval, validating Einstein's predictions. These observations reveal that time is relational, dependent on motion and gravitational context, rather than an independent absolute. The perception of sequential flow is an emergent phenomenon, rooted in neural processes and reinforced by the directionality of entropy. Entropy itself provides a bridge between the static block universe and the lived experience of temporal progression. The early universe, evidenced by the uniformity of the cosmic microwave background, began in a remarkably low entropy state. As the cosmos expands, systems evolve toward higher entropy, generating irreversible processes. This growth of disorder defines the arrow of time, giving the brain a framework for memory, anticipation, and decision-making. Our perception of moments flowing from past to future is therefore grounded in statistical mechanics. The increase of entropy creates a gradient along which conscious experience can be organized. Even in a universe where all events coexist, entropy ensures that sequences have direction, shaping cognition and perception, without altering the underlying geometric reality. Relativity and the block universe also illuminate extreme cosmic phenomena. Near black holes, time slows dramatically relative to distant observers. An astronaut falling toward an event horizon would experience seconds while years pass outside, illustrating the profound malleability of time under gravity. Gravitational lensing, verified through observations of starlight bending around massive objects, further confirms the interdependence of space and time. These effects demonstrate that time is not a universal river, but a local dimension influenced by mass and motion. Consciousness experiences continuity, yet the underlying structure is geometric, indifferent, and complete, containing all events as fixed coordinates in the space-time manifold. The implications of this view extend beyond physics into philosophy and cognition. Free will remains a lived experience, yet in the block universe, choices trace paths through existing coordinates rather than creating new moments. Causality persists, as sequences of events are ordered along the manifold and constrained by light cones and space-time geometry. The human mind perceives a narrative, but the cosmos itself is timeless in structure, providing a stable framework in which consciousness navigates. Memory, anticipation, and attention shape subjective experience, reinforcing the illusion of flow, while physical reality remains invariant, confirming that the universe does not require a moving present to function or evolve. As the chapter concludes, the stage is set to explore why, despite the static nature of space-time, humans perceive a direction to time. Entropy, thermodynamics, and statistical mechanics combine to create the arrow of time, bridging the geometric reality of the block universe with the subjective experience of a flowing present. This interplay between physical law and consciousness reveals the dual nature of time, a dimension integrated with space, and a construct emergent from cognition. The insights of Einstein, Minkowski, and experimental physics prepare us to examine this arrow in detail, to understand why we feel moments passing, and to explore how the universe reconciles geometric timelessness with lived experience. Time is at once a coordinate and a perception, a dimension of space and an illusion of consciousness, awaiting deeper exploration into its direction, emergence, and ultimate fate. The concept of the block universe challenges our deepest intuitions about existence and change. In everyday life, we experience time as a flowing river, carrying us from a remembered past to an anticipated future. We speak of moments passing, of yesterday fading, and tomorrow arriving, as though time itself were in motion. Yet physics, guided by Einstein's theories of relativity and Minkowski's geometric formulation, paints a different picture. In the four-dimensional manifold of spacetime, all events past, present, and future exist simultaneously as fixed coordinates. The universe is not a stage upon which events unfold, but a landscape in which they are embedded. Consciousness, navigating this landscape, constructs the sensation of progression, creating the illusion of a flowing now from the static fabric of reality. Relativity undermines the notion of a universal present. Two observers moving relative to each other may disagree on the order of events, experiencing a different sequence of moments while remaining consistent within the laws of physics. What is simultaneous for one is sequential for another, revealing that the division of time into past, present, and future is observer-dependent. This relativity of simultaneity forms the foundation of the block universe interpretation, where the entire history and future of the cosmos coexist. In this framework, every experience, every event, every choice occupies a coordinate within space-time. Our sense of temporal flow is not evidence of a moving river of time, but a feature of cognition, a method by which conscious minds integrate, sequence, and interpret the vast tapestry of events around them. The philosophical implications are profound. If all moments coexist, then the past is not gone, and the future is not yet to be created. They are fixed within the four-dimensional manifold, waiting to be accessed by consciousness. This view does not deny free will. Rather, it reframes it. Choices are experienced sequentially, yet they exist as coordinates within space-time. Causality persists, guided by the light cones and geometric structure that define which events can influence others. The universe is deterministic in its structure, but the experience of decision-making and creativity remains real. Consciousness traces a path through the manifold, giving rise to the sensation of movement, change, and narrative, while the underlying structure is timeless, complete, and indifferent to perception. Entropy provides a bridge between the block universe and lived experience. While space-time is symmetric and contains all events, physical processes within it are asymmetric due to the second law of thermodynamics. The early universe began in a state of extraordinarily low entropy, as evidenced by the cosmic microwave background, and has been evolving toward higher entropy ever since. This progression defines the arrow of time, creating a preferred direction along which sequences unfold. Memory, attention, and cognition are structured by this gradient, allowing conscious beings to interpret events in a coherent order. Even in a static four-dimensional manifold, the growth of entropy gives rise to the subjective sensation of past and future, aligning perception with physical law. The flow of time emerges not from the universe itself, but from the interplay of geometric structure and thermodynamic directionality. Black holes provide some of the most striking illustrations of the block universe in action. Near the event horizon, time slows dramatically relative to distant observers. An astronaut falling toward the black hole experiences seconds, while years pass outside. Light escaping the gravitational well is redshifted, demonstrating the curvature of space-time and the malleability of temporal intervals. These extreme conditions reveal that time is a local dimension, influenced by gravity and motion, rather than a universal backdrop. Every event, every path through space-time is embedded in the manifold. Consciousness interprets sequences, constructing narratives of past, present, and future, while the underlying reality remains static and all-encompassing. The universe contains all coordinates simultaneously, and the experience of moving through time is a projection of awareness onto this geometric stage. Experimental confirmations reinforce the block universe view. Time dilation observed in high-energy particle experiments, atomic clock flights, and gravitational redshift measurements consistently align with predictions derived from relativity. Satellites must adjust for both relative motion and gravitational influence to provide accurate positioning. Mercury's orbit and other planetary phenomena conform to the geometric framework of spacetime. These observations demonstrate that time is relational and observer-dependent, not absolute. The human sensation of flow is an emergent property of consciousness, intertwined with memory, anticipation, and statistical mechanics, yet independent of the four-dimensional structure that hosts all events. The universe, in this perspective, is a static manifold containing every instant, every occurrence, and every trajectory, revealing a reality far stranger than perception alone can suggest. The block universe also reframes our understanding of causality and determinism. Events influence one another within the constraints of spacetime geometry, bounded by light cones that define which events can be causally connected. Choices, actions, and consequences are sequences along paths traced by conscious entities, but these paths exist within a fixed structure. Determinism applies to the coordinates themselves, yet consciousness experiences variability and decision-making as it navigates the manifold. Memory records sequences, anticipation projects possibilities, and cognition interprets patterns, all within the context of a universe where every coordinate already exists. The interplay between perception and geometry creates the lived experience of time, providing order, meaning, and coherence to consciousness, while remaining entirely consistent with the physical structure of reality. Entropy and the arrow of time anchor the block universe to the lived experience of sequential moments. While the manifold of spacetime is symmetric, physical processes exhibit asymmetry due to the second law of thermodynamics. The early universe, as revealed by the cosmic microwave background, began in an extraordinarily low entropy state. From that primordial order, systems have evolved toward higher entropy, producing irreversible processes. This progression defines a temporal gradient, giving conscious observers a framework for organizing events. Memory formation, perception of cause and effect, and the anticipation of future outcomes are all shaped by this directionality. The universe may contain all events simultaneously, yet the growth of entropy ensures that sequences unfold in a manner consistent with experience, allowing the brain to interpret and navigate the manifold coherently. Experimental confirmations of time's relativity support this perspective. Muons generated by cosmic rays survive longer when moving at near light speeds, consistent with time dilation predicted by special relativity. Atomic clocks flown on aircraft and satellites reveal discrepancies in elapsed time due to both motion and gravitational potential. Gravitational redshift, observed in photons escaping massive bodies, confirms that time slows in stronger gravitational fields. Mercury's orbit, accurately predicted by general relativity, demonstrates how spacetime curvature governs the motion of celestial bodies. Each of these observations reinforces the view that time is relational, local, and observer-dependent, rather than an absolute flow. Consciousness experiences a sequential narrative, but the underlying structure is a four-dimensional manifold, static and complete, containing every event. Perception of temporal flow emerges from the interaction between consciousness and physical law. Neural mechanisms integrate sensory information over discrete intervals, producing continuous experience. The brain records events, anticipates consequences, and constructs narratives, all within the context of entropy-driven processes. Attention, emotion, and memory shape the subjective pace of time, stretching moments of fear and compressing monotonous intervals. Temporal illusions, such as the oddball effect or chronostasis, reveal that perception is flexible and constructed, further emphasizing that the sensation of flow is an emergent property rather than a fundamental feature of the cosmos. The block universe provides a stable geometric backdrop, while the arrow of time and neural processing generate the lived experience of progression. Black holes and extreme gravitational environments exemplify the flexibility of time as a dimension. Approaching an event horizon, time slows relative to distant observers, and light, escaping the gravitational well, is increasingly redshifted. An observer falling into the black hole experiences seconds, while years elapse elsewhere. These phenomena illustrate that time is a local coordinate influenced by mass and motion. Every event, including the trajectories of particles and the decisions of conscious beings, exists within the space-time manifold. Consciousness interprets sequences along paths, constructing a narrative while remaining fully compatible with the static structure. In this context, the block universe reconciles the coexistence of all events with the subjective experience of change, demonstrating that flow is a cognitive interpretation rather than a property of space-time itself. The philosophical consequences extend to causality and determinism. Within the manifold, events are connected according to space-time geometry, bounded by light cones that dictate which events can influence one another. Determinism applies to the coordinates and the structure of space-time, yet consciousness experiences variability, choice, and creativity as it traces paths through the manifold. Memory and anticipation provide coherence and meaning, organizing experience into sequences. The universe accommodates both the geometric certainty of the block universe and the subjective flexibility of cognition. Free will is not negated, but recontextualized. Decisions are experienced sequentially, even though the coordinates of those decisions already exist within space-time. The interplay between perception and geometry creates the familiar sensation of past, present, and future, anchoring consciousness while remaining fully consistent with physics. Relativity, entropy, and the block universe collectively redefine our understanding of existence. Time is a dimension intertwined with space, and all events are embedded within a four-dimensional manifold. The arrow of time, shaped by entropy, provides a directional gradient for consciousness to interpret. Neural processes generate the perception of flow, narrative, and causality, while the physical universe remains static and complete. This synthesis of geometry, thermodynamics, and cognition explains why humans experience a moving present in a universe where all moments exist. It reconciles the apparent contradiction between the block universe and lived experience, offering a coherent framework in which perception, physics, and philosophy intersect. Consciousness navigates space-time, creating the sensation of time passing, even though the coordinates themselves are fixed, eternal, and indifferent to observation. As we conclude this part, the stage is set to examine deeper consequences for understanding free will, determinism, and the nature of existence within the block universe. The next exploration will consider how the arrow of time, rooted in entropy and cosmology, interacts with consciousness, shaping experience while respecting the underlying geometry. Time, from this perspective, is both a dimension and a perception, a fixed coordinate and an emergent narrative, a reality that is simultaneously complete and alive. The block universe challenges intuition, yet it provides a consistent, evidence-based framework for reconciling physics, cognition, and philosophy, opening the path to explore why we feel time flowing even when the cosmos itself does not move. The arrow of time emerges as a crucial link between the static block universe and the dynamic experience of consciousness. While all events exist within space-time, physical processes unfold in a preferred direction due to the second law of thermodynamics. Entropy increases, creating an irreversible gradient along which sequences are experienced. This thermodynamic asymmetry provides structure to memory, perception, and anticipation, allowing the mind to organize events coherently. We remember the past, but not the future, and we anticipate outcomes based on the accumulation of information. This asymmetry explains why the brain perceives progression even within a manifold where every coordinate is fixed. The flow of time is thus a property of emergent systems interacting with the statistical behavior of matter, rather than a fundamental feature of the universe itself. Neuroscience supports this understanding by revealing how the brain integrates temporal information. Neurons encode events across milliseconds to seconds, constructing continuous experience from discrete signals. The basal ganglia, cerebellum, and prefrontal cortex coordinate timing, anticipation, and motor planning, enabling humans to act coherently in a world structured by physical law. Temporal illusions demonstrate the malleability of perception. The oddball effect, chronostasis, and other cognitive phenomena show that the mind flexibly interprets intervals, stretching or compressing subjective duration. The sensation of moving through time is generated by these processes, while the underlying spacetime remains static. Consciousness navigates the block universe, tracing trajectories through coordinates, creating narrative continuity, and reinforcing the illusion of a flowing present. Extreme astrophysical environments further illustrate the relativity and malleability of time. Near black holes, gravitational time dilation is profound. From a distant perspective, an infalling object appears to freeze at the event horizon, while the object itself experiences time normally. Light escaping from such regions is increasingly redshifted, showing the influence of space-time curvature on temporal intervals. These phenomena confirm that time is not universal. It depends on local geometry, mass, and motion. The universe contains all events simultaneously, yet consciousness experiences sequences shaped by entropy and neural processing. Observers navigate their paths, integrating experiences in ways that align with the statistical directionality of time, producing the familiar sensation of past, present, and future. The philosophical implications are striking. Free will, determinism, and causality exist within the context of a fixed manifold. Events are interconnected according to light cones and space-time geometry, ensuring consistent, causal relationships. Consciousness experiences choice sequentially, yet all coordinates are embedded within the four-dimensional structure. The block universe does not negate agency, it reframes it. Paths traced by observers reflect decisions experienced in order, even though the coordinates themselves are eternal. Memory and anticipation provide continuity and meaning, allowing perception to construct coherent narratives. Physics defines the stage, entropy provides direction, and consciousness interprets the journey, integrating these elements into the lived experience of temporal flow. The block universe also challenges our understanding of cosmology and existence. Time is a dimension, inseparable from space, and all events coexist. Relativity demonstrates that motion and gravity shape intervals, while entropy creates a directional gradient. Consciousness perceives sequences, constructs memory, and anticipates outcomes, generating the vivid experience of passage. The interplay between these factors reconciles the apparent contradiction between the geometric timelessness of space-time and the dynamic sensation of lived reality. The universe is both static and complete, and yet the mind navigates it as though moving, creating the illusion of flow while remaining fully consistent with evidence. The block universe, thermodynamics, and neural processing together provide a comprehensive framework for understanding time as both a dimension and a perception. As this chapter concludes, the stage is prepared for the next exploration: the arrow of time, thermodynamics, and quantum effects that reinforce the perception of directionality. Understanding how irreversible processes emerge from fundamental laws will illuminate why consciousness experiences past, present, and future, despite the coexistence of all events in the block universe. The journey ahead will bridge geometric spacetime, statistical mechanics, and neuroscience, revealing the intricate interplay between physics and perception. Time, in this perspective, is simultaneously an immutable coordinate, a statistical emergent property, and a cognitive experience, a multi-dimensional phenomenon whose nature challenges intuition while remaining firmly grounded in evidence. The block universe opens the door to understanding the universe as a complete, eternal structure, navigated by consciousness in a dance of perception and physics, setting the foundation for exploring the origins, direction, and ultimate fate of time. The sensation that time moves in a single direction is one of the most familiar aspects of human experience. We remember the past, anticipate the future, and perceive a continuous progression from one moment to the next. Yet physics reveals a more nuanced reality. At the fundamental level, many laws governing particles and forces are time-symmetric. Newtonian mechanics, electromagnetism, and even quantum interactions in isolation often function identically if the direction of time is reversed. A collision of billiard balls would proceed plausibly backward, and the equations describing planetary motion allow for reversal without contradiction. Despite this symmetry, the macroscopic world we inhabit exhibits a pronounced directionality. Eggs break, but do not unbreak. Heat flows from hot to cold, and humans age rather than rejuvenate. This asymmetry, the arrow of time, emerges from statistical behavior, thermodynamics, and the initial conditions of the cosmos, providing the framework within which consciousness perceives flow. Entropy lies at the heart of this asymmetry. Ludwig Boltzmann formulated the insight that the second law of thermodynamics is statistical in nature. Systems evolve from low probability, ordered states toward high probability, disordered states. An isolated box of gas molecules begins in a configuration with few constraints, but over time the molecules spread, filling the available volume, increasing disorder. The likelihood of all molecules spontaneously returning to a previous ordered arrangement is vanishingly small. The arrow of time, therefore, arises not from fundamental forces, but from probability. The universe began in a state of extraordinarily low entropy, and as it evolves toward higher entropy, irreversible processes emerge. This statistical foundation explains why certain sequences are observed consistently in one direction, forming the experiential backbone of temporal flow. Observations of the cosmic microwave background provide evidence for the low entropy state of the early universe. 1965 saw its discovery, revealing a remarkably uniform radiation field permeating space. This uniformity indicates that the early cosmos was highly ordered, setting the initial conditions that allow entropy to increase over time. Without this initial low entropy state, the directionality of thermodynamic processes would be arbitrary, and the arrow of time, as we perceive it, would not exist. Cosmology thus grounds the temporal asymmetry in the large-scale structure of the universe, linking the flow of human experience to the statistical and geometric properties of space-time. The early universe imprinted a gradient along which processes unfold, shaping memory, perception, and causality. Loschmidt's paradox, posed by Joseph Loschmidt, highlights the tension between time-symmetric microscopic laws and the observed macroscopic directionality. If the fundamental laws of motion are reversible, why does entropy increase? The resolution lies in initial conditions and statistical improbability. While microscopic interactions allow reversals, the probability of an entire system spontaneously decreasing in entropy is extraordinarily small. Boltzmann's insight reconciles microscopic symmetry with macroscopic irreversibility. Thermodynamic processes almost always proceed toward disorder, generating the arrow of time that structures sequences and experiences. Consciousness interprets these sequences as a flowing present, embedding narrative, causality, and memory within the statistical framework dictated by the universe. Time asymmetry is reinforced by cosmological expansion. As the universe grows, the overall energy density decreases, matter spreads, and entropy continues to increase. Stars fuse elements, planets evolve, and life develops in environments far from thermodynamic equilibrium, exploiting gradients to maintain order locally while contributing to overall entropy growth. The arrow of time is manifest in these processes, observable from galactic dynamics to the biological cycles that structure life. Quantum mechanics, while largely time-symmetric in its fundamental equations, contributes probabilistically to this asymmetry through decoherence. When quantum systems interact with their environments, superpositions resolve into definite outcomes, generating apparent irreversibility. Entropy, cosmology, and quantum statistics collectively define the one-way nature of macroscopic change, bridging the block universe with lived experience. Black holes further exemplify the interplay between time, entropy, and directionality. The laws of black hole thermodynamics, developed by Stephen Hawking and Jacob Bekenstein, link surface area to entropy, establishing that even in extreme gravitational environments, entropy increases and an arrow of time persists. Hawking radiation allows black holes to emit particles, gradually decreasing mass while increasing overall entropy of the surrounding space. These processes confirm that thermodynamic directionality remains a fundamental aspect of cosmic evolution. Even as spacetime contains all events, local interactions and energy flows create sequences experienced as irreversible by observers, embedding the arrow of time within the four-dimensional manifold. The human brain interprets these sequences through neural computation. Temporal integration combines events over milliseconds to seconds, generating continuity and coherence. Memory records the past, allowing anticipation of the future, while attention focuses perception on unfolding sequences. Temporal illusions demonstrate the flexibility of perception, yet they do not alter the underlying thermodynamic asymmetry that structures events. Consciousness navigates this gradient, experiencing flow, sequence, and causality, while the block universe provides the complete geometric substrate. The arrow of time, arising from entropy, cosmology, and quantum interactions, ensures that these experiences are consistent and ordered, aligning subjective sensation with the physical structure of reality. Gravity profoundly influences the arrow of time, intertwining space-time geometry with thermodynamic directionality. According to general relativity, massive objects curve space-time, affecting the flow of time locally. Clocks closer to a massive body tick more slowly relative to distant observers, a phenomenon confirmed experimentally by the Pound-Rebka experiment and through precise measurements of satellite systems. Near black holes, this effect becomes extreme, with time approaching a standstill at the event horizon from an external perspective. Despite this relativistic slowing, entropy continues to increase locally, ensuring that irreversible processes persist. Gravitational time dilation thus interacts with thermodynamic gradients, shaping the sequences of events and reinforcing the arrow of time in both familiar and extreme environments. Quantum mechanics adds another layer of complexity to temporal asymmetry. While the Schrödinger equation is fundamentally time-symmetric, interactions with the environment cause decoherence, collapsing superpositions into definite outcomes. This process generates apparent irreversibility at the macroscopic level, aligning quantum events with the thermodynamic arrow of time. Experiments in quantum optics demonstrate that entanglement between subsystems can give rise to emergent temporal order, linking the behavior of individual particles to the broader directional structure of the universe. Although quantum mechanics alone does not prescribe an arrow, its interplay with entropy and environmental interactions ensures that observers perceive a consistent sequence of events, allowing conscious experience to align with statistical and relativistic constraints. Thermodynamic irreversibility is not confined to cosmic or quantum scales. It is evident in everyday phenomena. Heat spontaneously flows from hot to cold. Gases expand to fill available volume, and chemical reactions proceed toward equilibrium. These processes are manifestations of microscopic interactions aggregated over vast numbers of particles, governed by probabilities that overwhelmingly favor increased entropy. Loschmidt's paradox reminds us that the microscopic laws allow reversals, yet the likelihood of macroscopic decrease in entropy is vanishingly small. This probabilistic certainty underpins the arrow of time, providing a bridge between fundamental physics and human experience. Consciousness interprets these processes as a one-way flow, reinforcing the perception of past and future. The brain itself is tuned to perceive temporal sequences in alignment with these physical principles. Neural circuits integrate sensory information over discrete intervals, forming continuous perception and coherent narratives. The basal ganglia, cerebellum, and prefrontal cortex, coordinate timing, anticipation, and decision-making. Memory stores past events, providing context for interpreting the present, while attention directs focus to ongoing processes. Temporal illusions, such as the oddball effect and chronostasis, reveal that perception is constructed and flexible, yet always anchored to the arrow defined by entropy. Even in altered subjective experiences, the underlying thermodynamic and relativistic structure preserves the directionality that informs cognition and action. Cosmology reinforces the inevitability of the arrow of time on the grandest scales. The universe's expansion, evidenced by redshift measurements of distant galaxies and the cosmic microwave background, sets boundary conditions that dictate entropy increase. Stars fuse elements, planets form and evolve, and life emerges by exploiting energy gradients far from equilibrium. Over cosmological timescales, the universe continues toward higher entropy, approaching a state of maximum disorder. This progression ensures that sequences of events, from microscopic interactions to galactic evolution, exhibit directionality consistent with human experience. The arrow of time emerges from initial conditions, statistical mechanics, and cosmology, linking perception, thermodynamics, and geometry in a coherent framework. Even in the context of the block universe, the arrow of time remains meaningful. While all events exist as coordinates within the manifold, entropy imposes a preferred direction along which processes unfold. Consciousness experiences this gradient as flow, sequence, and causality. Memory records past states, anticipation projects future possibilities, and neural computation integrates discrete events into coherent experience. The interplay between geometric structure, thermodynamic gradients, and cognitive architecture reconciles the timeless nature of spacetime with the apparent one-way progression of events. Observers navigate the manifold, interpreting sequences in a manner consistent with entropy, gravity, and quantum interactions, creating a unified experience of temporal flow grounded in physical reality. Extreme environments such as black holes, neutron stars, and rapidly moving frames provide compelling illustrations of these principles. Relativistic time dilation, gravitational redshift, and quantum decoherence interact with entropy to maintain the arrow of time, even under conditions vastly different from terrestrial experience. Observers in these regimes would perceive sequences consistent with local thermodynamic and geometric constraints, demonstrating the universality of directional processes. Despite the static coordinates of the block universe, irreversible phenomena occur. Neural systems interpret sequences, and the arrow of time persists as a consistent feature of macroscopic reality. The convergence of relativity, thermodynamics, quantum mechanics, and consciousness establishes a comprehensive framework for understanding why events unfold in a single direction, reconciling intuition with evidence. The arrow of time shapes causality and the unfolding of events across all scales. In the block universe, all coordinates exist, yet the increase of entropy dictates which sequences are observed and experienced. Causal relationships follow the gradient imposed by statistical mechanics, ensuring that causes precede effects and that processes are irreversible. Heat flows, chemical reactions proceed, and biological systems develop in one direction, establishing a consistent temporal order. Consciousness interprets these sequences as narrative, integrating memory, anticipation, and attention to construct a coherent perception of events. The arrow of time bridges the static manifold of spacetime with lived experience, aligning observation with the probabilistic structure of the universe. Free will, determinism, and choice are reframed by the arrow of time. While the coordinates of every event exist within the block universe, entropy and thermodynamic gradients structure sequences in which decisions are experienced. Conscious beings navigate these paths, perceiving options and consequences, and memory reinforces the sense of past and future. Determinism applies to the manifold's geometric structure, yet the emergent arrow of time allows sequences to be experienced consistently. The mind interprets probabilistic events and irreversible processes as coherent narratives, creating the lived reality of decision-making and causality, while remaining fully consistent with physical law. The arrow of time thus mediates between geometric timelessness and experiential flow, providing a foundation for agency within the static cosmos. Black holes exemplify the integration of entropy, gravity, and temporal asymmetry. As matter falls toward the event horizon, time slows relative to distant observers, yet local processes, including thermodynamic interactions, continue along their arrow. Hawking radiation allows black holes to emit particles, increasing overall entropy despite the extreme curvature of spacetime. These phenomena confirm that irreversible processes persist even under conditions of extreme time dilation, reinforcing the universality of the arrow. Observers, whether near massive bodies or in ordinary environments, experience sequences consistent with thermodynamic gradients, ensuring that causality, memory, and perception maintain coherent directionality within the block universe. The interplay between relativity, entropy, and consciousness reconciles extreme physics with everyday experience. Quantum decoherence provides a microscopic mechanism for the arrow of time. Superpositions of states, when interacting with the environment, collapse into definite outcomes, generating apparent irreversibility. While the fundamental equations are symmetric, interactions with surroundings induce temporal asymmetry, linking microphysics to macroscopic phenomena. Experiments in quantum optics demonstrate that entanglement between subsystems can produce emergent temporal order, illustrating how statistical mechanics and quantum dynamics converge to establish the arrow. Consciousness perceives sequences of events shaped by these processes, integrating outcomes into coherent narratives, further reinforcing the subjective sensation of time's flow within a fundamentally static manifold. The human brain operates as a temporal integrator, tuned to interpret the arrow of time. Neurons encode discrete events, coordinating through milliseconds to seconds to create continuous experience. Memory stores prior states, enabling anticipation and prediction, while attention focuses perception on unfolding sequences. Temporal illusions reveal that perception is malleable yet anchored by the physical gradient of entropy. The arrow of time is both external and internal. It is the statistical behavior of matter and energy, and it is the framework through which neural computation organizes experience. This alignment between external physical law and internal cognitive processing ensures that subjective time matches the directionality imposed by the universe. Cosmology amplifies the arrow on the largest scales. The universe's expansion drives entropy increase, guiding the evolution of stars, galaxies, and planetary systems. Life exploits energy gradients, developing complexity locally while contributing to global entropy growth. As entropy approaches a maximum, the arrow of time ensures that events continue to unfold in a consistent direction, maintaining causal order and supporting coherent perception. Conscious observers experience this gradient as flow, narrative, and progression, while the block universe contains all events as fixed coordinates. The interplay of cosmic expansion, thermodynamics, and neural computation integrates geometric, statistical, and experiential dimensions into a unified understanding of temporal directionality. As Chapter 4 concludes, the arrow of time emerges as a multifaceted phenomenon, connecting fundamental physics, cosmology, quantum mechanics, and consciousness. Entropy, initial conditions of the universe, gravitational effects, and quantum interactions establish directionality. Neural systems interpret sequences, creating the sensation of past, present, and future. This comprehensive framework reconciles the static structure of spacetime with lived experience, providing a coherent explanation for why time feels unidirectional. The stage is now set to explore the next frontier: how extreme space-time curvature, black holes, and gravitational effects shape time itself, revealing the subtle interplay between geometry, physics, and perception that defines the behavior of temporal dimensions in our universe. Gravity is not merely a force pulling objects together. It is the curvature of space-time itself. Einstein's general relativity transformed our understanding of gravity from a mysterious attraction to a geometric property of the universe. Mass and energy bend the fabric of space-time, and this curvature dictates the motion of objects and the flow of time. Near massive bodies, clocks tick more slowly relative to distant observers, a phenomenon called gravitational time dilation. Experiments have confirmed this effect repeatedly, from the Pound-Rebka experiment measuring redshift of photons on Earth to the adjustments required for the global positioning system. Time, once thought universal and absolute, is local and malleable, intertwined with the presence of matter and the geometry of space. Black holes represent the most extreme demonstration of curved space-time. These regions, formed from the collapse of massive stars, contain gravitational fields so strong that nothing, not even light, can escape beyond the event horizon. For an observer falling toward a black hole, time proceeds normally along their trajectory, yet a distant observer perceives their descent as slowing indefinitely. Light emitted from near the horizon is increasingly redshifted, demonstrating the profound warping of temporal intervals. These extreme conditions reveal that time is not uniform. It is shaped by the curvature of space-time, influenced by mass, energy, and the observer's position. Every event, every path through space-time, is embedded within this geometry, yet the experience of time is locally variable, highlighting the relativity of duration and simultaneity. The concept of a singularity challenges classical physics. At the center of a black hole, general relativity predicts that curvature becomes infinite and conventional equations break down. Time as understood classically ceases to exist in meaningful terms, and space collapses to a point. While no observer can witness a singularity directly, its implications are profound. It represents a boundary where our current understanding of physics cannot describe the behavior of matter, energy, or time itself. Hawking and Bekenstein demonstrated that black holes have entropy and emit radiation, linking these extreme objects to thermodynamics. Hawking radiation allows black holes to lose mass over incredibly long timescales, showing that even the most warped regions of spacetime are subject to the arrow of time and statistical laws. Gravitational time dilation is not confined to black holes. Any massive body, including planets and stars, warps spacetime and alters the rate at which time passes. Satellites in orbit around Earth experience both velocity-based and gravitational time dilation, requiring adjustments to remain synchronized with ground-based clocks. Without these corrections, global positioning systems would quickly become inaccurate. The curvature of space-time ensures that time is relative, measured locally, and influenced by both motion and mass. Observers in different gravitational potentials experience sequences of events differently, yet the underlying structure of spacetime contains all events, fixed within a four-dimensional manifold. Consciousness interprets these sequences locally, constructing a coherent narrative while remaining embedded in the global geometry. Extreme curvature also affects causality and simultaneity. In flat spacetime, light cones define the causal structure, determining which events can influence others. Near massive objects, these light cones tilt, altering the relationship between cause and effect as perceived by distant observers. Events that are simultaneous in one frame are not simultaneous in another, emphasizing that simultaneity is relative, dependent on the observer's position and motion. In regions near black holes or neutron stars, this effect is pronounced, demonstrating that the passage of time is not uniform across the cosmos. Despite these variations, entropy continues to increase locally. preserving the arrow of time and providing a consistent framework for perception, memory, and causality within the curved geometry. The curvature of time influences energy, motion, and the evolution of systems. Particles and light follow geodesics, the natural paths dictated by space-time geometry. Orbits around massive bodies are determined not by force alone, but by the shape of the manifold itself. Light bending around stars, time delays in signals passing near massive objects, and precession of planetary orbits are all manifestations of curved space-time. These phenomena are not abstract. They define the operational meaning of time in the universe. Observers measure intervals by motion, frequency, and decay, all of which are influenced by local curvature. Conscious experience is situated within this framework, interpreting temporal sequences relative to local geometry and physical law. Black holes also illuminate the connection between curvature, thermodynamics, and quantum theory. Their entropy is proportional to the area of the event horizon, linking geometric properties to statistical mechanics. Hawking radiation, arising from quantum effects near the horizon, demonstrates that extreme curvature can produce particle emission, a process that respects the arrow of time while revealing the interplay between general relativity and quantum physics. These insights suggest that time, while locally experienced as flowing, is globally structured by curvature, entropy, and quantum phenomena. The universe contains all events in the block universe, yet the local rate and sequence of these events are shaped by mass, energy, and geometry. Neural systems interpret temporal sequences against this backdrop of curvature and variation. Humans experience seconds, minutes, and hours as coherent intervals, despite the relativistic variability of time in the broader cosmos. Memory, attention, and anticipation integrate these intervals into continuous perception, providing a stable framework for action and cognition. Even when physical time varies locally due to gravitational effects, the brain constructs narratives that maintain coherence, ensuring that perception aligns with operational time. The curvature of space-time defines the structure of reality, while consciousness interprets it through local experience, harmonizing physical law with lived sensation. As this part concludes, the stage is set to explore deeper consequences of curved time, singularities, and the interplay with quantum phenomena. The next section will examine how time behaves near the most extreme objects, including the limits of classical equations, the emergence of Hawking radiation, and the profound implications for the nature of temporal dimensions. Understanding curved time is essential for reconciling relativity, thermodynamics, and quantum mechanics, and for appreciating how the universe accommodates both fixed events and locally experienced flow. Extreme environments such as black holes and neutron stars reveal the profound interplay between space-time curvature, entropy, and quantum mechanics. Singularities, predicted at the centers of black holes, represent regions where classical physics breaks down. Time, as a measurable quantity, loses conventional meaning, and space collapses to a point of infinite density. While these regions are inaccessible to direct observation, theoretical analysis indicates that the laws governing matter, energy, and temporal intervals reach limits beyond which our current understanding cannot extend. Hawking and Bekenstein showed that black holes are not inert. They possess entropy proportional to the area of the event horizon, connecting geometric properties to thermodynamic behavior. Hawking radiation allows black holes to emit particles, demonstrating that even under extreme curvature, irreversible processes occur, and the arrow of time persists. Quantum effects near event horizons blur the distinction between classical and emergent time. Vacuum fluctuations generate particle-antiparticle pairs, some of which escape as radiation, while others fall into the singularity. This process reduces black hole mass over extraordinarily long timescales, linking microscopic quantum phenomena to macroscopic thermodynamic evolution. Entropy increases as the universe absorbs energy emitted by the black hole, reinforcing the directional flow of time, even in extreme regions, where relativistic effects slow local processes relative to distant observers. Curved spacetime, quantum mechanics, and statistical physics converge to maintain consistency, demonstrating that the arrow of time is universal. Yet locally experienced rates of progression vary dramatically, depending on gravitational potential and motion. The relativity of simultaneity becomes striking in these environments. Observers at different positions relative to a massive body perceive events in divergent orders. Near an event horizon, the external universe appears to evolve rapidly, while local processes proceed normally for the infalling observer. Light from distant events is redshifted, and intervals measured locally differ from those measured by remote observers. This relativity does not contradict the block universe. All events exist as coordinates, but the perception of order and duration depends on local conditions. Consciousness integrates these sequences according to local experience, creating coherent narratives despite variations in temporal rate imposed by spacetime curvature. The arrow of time, dictated by entropy, ensures consistency across scales, connecting neural perception to cosmic processes. Gravitational time dilation also affects energy and motion. Particles and light follow geodesics, which bend near massive bodies. Signals traveling near black holes experience delays, and clocks in orbit or near dense stars require adjustments to remain synchronized. These effects are not merely theoretical. They have practical implications for navigation, communication, and the measurement of fundamental constants. The universe's structure dictates local rates of time, yet the geometric manifold encompasses all events, allowing for consistent description across frames. Conscious observers interpret sequences relative to local time, integrating curvature, motion, and energy flow into perception, maintaining coherence in both action and memory. Black hole thermodynamics illuminates the deeper connection between curvature and statistical physics. The entropy of a black hole, encoded in its surface area, implies that information is stored on the event horizon. Hawking radiation results from quantum fluctuations, producing energy emission and gradual mass loss. These processes confirm that curved spacetime interacts with thermodynamic laws, preserving the arrow of time and providing a mechanism for irreversible evolution. Even in extreme curvature, time retains its statistical and experiential directionality, ensuring that sequences unfold consistently for local observers. Consciousness perceives these sequences as continuous and coherent, integrating the local rate of events with broader physical law. Neural processing remains attuned to local temporal experience, even in hypothetical extreme conditions. The brain encodes events over milliseconds to seconds, forming narratives that maintain continuity regardless of global relativistic effects. Memory stores prior states, anticipation predicts outcomes, and attention structures perception. Temporal illusions demonstrate flexibility, yet local experience always aligns with thermodynamic and geometric constraints. The arrow of time ensures that sequences of events are interpretable, coherent, and causally consistent, allowing observers to navigate complex environments while maintaining a sense of past, present, and future. Curvature modifies local experience, but does not negate the fundamental directionality imposed by entropy and statistical mechanics. Cosmological implications extend beyond individual black holes. The universe contains vast regions of varying mass, energy, density, and curvature. Stars, galaxies, and clusters warp spacetime, influencing the local flow of time, while the global block universe encompasses all coordinates. Entropy increases universally, establishing a statistical gradient that defines the arrow of time. Consciousness interprets local sequences relative to this gradient, integrating curvature, quantum effects, and thermodynamic behavior into coherent perception. The convergence of geometry, entropy, and cognition reconciles extreme physics with human experience, providing a consistent framework in which the local sensation of flow coexists with a static four-dimensional manifold. As this part concludes, the foundation is laid for the final section of the chapter. The next exploration will examine the limits of classical physics near singularities, the emergence of Hawking radiation, the interplay between curved spacetime and quantum phenomena, and the implications for understanding time as both local and global. The behavior of temporal dimensions in extreme gravitational fields offers profound insights into the nature of existence, linking relativity, thermodynamics, quantum mechanics, and consciousness into a unified understanding of curved time. Black holes and other regions of extreme curvature demonstrate the limits of classical physics, revealing where general relativity and quantum mechanics intersect. As matter approaches a singularity, space-time curvature intensifies, tidal forces stretch and compress objects, and the classical equations that describe gravity cease to provide meaningful predictions. Time, as a measurable interval, loses operational meaning, yet the statistical laws of thermodynamics continue to apply locally. Hawking radiation ensures that even in these extreme regimes, entropy increases, linking curvature to the arrow of time and maintaining the consistency of irreversible processes. Observers, whether hypothetically infalling or distant, perceive sequences of events in accordance with local conditions, illustrating the relative nature of temporal experience in the cosmos. The edge of spacetime is not a boundary in the traditional sense, but a domain where conventional coordinates and measurements reach their limits. Near singularities, the geometry of the universe becomes so distorted that paths through spacetime, or geodesics, are profoundly altered. Light cones tilt, causality is locally constrained, and intervals, measured by clocks, are dramatically affected. Yet the block universe encompasses these extremes, containing all events as coordinates within the manifold. Consciousness, however, interprets only locally accessible sequences, constructing coherent narratives from events within reachable light cones. The operational meaning of time emerges from interactions, motion, and observation, linking the fixed structure of spacetime with lived experience. Quantum phenomena near extreme curvature further complicate temporal understanding. Particle-antiparticle pairs produced by vacuum fluctuations contribute to Hawking radiation, reducing black hole mass over extraordinarily long periods. These emissions respect the arrow of time, ensuring that entropy continues to increase, even as the geometry of spacetime is stretched to its limits. The interplay between general relativity and quantum mechanics demonstrates that time is simultaneously local and emergent, dependent on curvature, energy, and environmental interactions. Sequences are experienced as flowing for local observers, while all events remain embedded in the geometric manifold, reconciling relativistic and quantum perspectives within a unified framework. Gravitational lensing and time delays illustrate the tangible effects of curvature on temporal measurement. Light passing near massive bodies follows bent paths, arriving at distant observers later than it would in flat spacetime. Signals between satellites, planets, and stars require corrections for both velocity and gravitational potential to maintain synchronization. These effects highlight that time is not a universal constant, but a local phenomenon shaped by geometry, motion, and energy. Human perception operates within these constraints, interpreting events according to local intervals, while being largely insensitive to extreme relativistic effects. The arrow of time, dictated by entropy, ensures that sequences are coherent and causally consistent, even across regions of varied curvature. Neural processing interprets temporal sequences relative to operationally defined intervals. The brain integrates discrete events, constructs continuous experience, and generates coherent narratives that align with both local physical law and statistical gradients. Memory, attention, and anticipation provide the scaffolding for temporal perception. allowing consciousness to navigate the manifold of events, even when local spacetime is highly curved. Temporal illusions reveal flexibility in perception, yet the underlying arrow remains anchored in entropy, causality, and statistical probability. This integration of cognition, thermodynamics, and curvature ensures that experienced time retains directionality, coherence, and consistency with physical principles. Extreme curvature also informs cosmological understanding. Black holes, neutron stars, and dense clusters warp spacetime on scales ranging from planetary to galactic. The universe contains all events in the block universe, yet local intervals, rates of progression, and perceived order are shaped by mass, energy, and geometry. Entropy continues to increase universally, preserving the arrow of time and ensuring consistent sequences of events for observers. Conscious experience aligns with these gradients, interpreting sequences relative to local conditions and neural processing. The convergence of curvature, quantum effects, and cognition provides a comprehensive understanding of how time behaves at the edge of spacetime, linking the extremes of physics with everyday perception. As Chapter 5 concludes, the behavior of curved time has been illuminated. Time is local, malleable, and intertwined with mass, energy, and geometry, yet statistical and thermodynamic principles preserve the arrow of time. Observers navigate sequences within the block universe, constructing coherent narratives despite variations in local intervals. Extreme gravitational fields, black hole thermodynamics, and quantum phenomena demonstrate the interplay between relativistic and statistical laws, revealing that time is both a dimension of spacetime and an emergent feature of interactions and perception. The next chapter will explore how quantum mechanics challenges classical notions of time, setting the stage for understanding the problem of time in fundamental physics and its implications for the nature of reality itself. Quantum mechanics, the framework governing the behavior of particles at the smallest scales, presents a radically different conception of time from classical physics. In quantum theory, time is typically treated as an external parameter, a backdrop against which systems evolve, rather than an observable that can be measured directly. The Schrödinger equation, which describes the evolution of a quantum state, relies on this external time to determine how wave functions change. Unlike position, momentum, or energy, time is not an operator with associated uncertainty. It provides the stage on which quantum events unfold. This distinction creates tension when attempting to reconcile quantum mechanics with general relativity, where time is inherently dynamic and intertwined with the curvature of spacetime. The measurement problem further complicates the understanding of time in quantum mechanics. A quantum system evolves deterministically, according to the Schrödinger equation, existing in a superposition of states. Observation, however, forces a collapse into a definite outcome, introducing an apparent asymmetry and an experiential directionality. Decoherence explains part of this phenomenon, showing that interactions with the environment effectively suppress interference between components of the superposition, producing classical outcomes. This process generates an arrow of time at the microscopic level, linking quantum evolution with statistical mechanics and the thermodynamic gradient, yet the underlying fundamental equations remain time-symmetric. The discrepancy between reversible laws and irreversible outcomes lies at the heart of the quantum conception of time. Attempts to unify quantum mechanics and general relativity give rise to the so-called problem of time. In canonical approaches to quantum gravity, such as the Wheeler-DeWitt equation, time disappears entirely from the formalism. The equation describes the quantum state of the entire universe, yet contains no explicit time variable, implying a timeless framework in which all configurations exist as possibilities. This counterintuitive result challenges conventional intuition, suggesting that time may be an emergent phenomenon rather than a fundamental entity. Ravelli and Kiefer, among others, have explored interpretations in which correlations between subsystems give rise to the appearance of temporal evolution, reconciling the timeless underlying equations with the flowing time experienced by observers. Emergent time models provide insight into how temporal experience might arise from a fundamentally static universe. The Page-Wouters mechanism, for example, proposes that entanglement between subsystems allows one part to serve as a clock for another, producing relational evolution. Within this framework, the global state of the universe is static, yet subsystems evolve relative to each other, generating sequences that align with perception. These models are fully consistent with the principles of quantum mechanics and general relativity, providing a bridge between the timeless formalism and lived experience. Experimental simulations in quantum optics have begun to explore these ideas, demonstrating that correlations between subsystems can mimic temporal evolution in controlled systems, though the scale and universality of such mechanisms remain subjects of ongoing research. The problem of time also illuminates the limits of operational definitions of temporal intervals in extreme contexts. Near singularities, in regions of high curvature, or in early cosmological epochs, conventional clocks lose meaning, and the distinction between past, present, and future becomes ambiguous. Quantum fluctuations, vacuum energy, and entanglement further complicate the definition of local time, showing that the flow of time is not intrinsic but contextual. Observers interpret sequences relative to local conditions, yet the global quantum state may remain static. This perspective challenges the classical notion of a universal temporal order, suggesting that the arrow of time, perception of duration, and causal sequences emerge from correlations, decoherence, and statistical behavior, rather than fundamental laws. Consciousness interprets sequences of events within the emergent temporal framework. Neural systems rely on regular intervals, memory, and attention to construct a coherent narrative of experience. Even in a fundamentally timeless quantum universe, observers perceive flow, causality, and progression because the brain integrates events relative to operational clocks and local interactions. The arrow of time, derived from entropy, thermodynamics, and correlations, ensures that perception aligns with experience, preserving the sense of past, present, and future. In this way, quantum mechanics, relativity, and cognition converge to produce a consistent phenomenology of time, even if the underlying reality is far removed from intuitive flow. The problem of time has profound implications for understanding cosmology, black holes, and the origins of the universe. In the earliest moments after the Big Bang, quantum fluctuations dominated, and classical spacetime had not yet emerged. Time as an external parameter was undefined, and sequences were determined by correlations between quantum subsystems. The evolution of the cosmos, from inflation to formation of stars and galaxies, can be seen as the unfolding of emergent temporal structures within a fundamentally static quantum state. Entropy increases, observers emerge, and the arrow of time becomes operationally meaningful, demonstrating how classical experience of flow arises from a deeper, timeless foundation. Quantum gravity deepens the problem of time by demonstrating that conventional notions of temporal progression are not universally applicable. The Wheeler-DeWitt equation, central to canonical quantum gravity, describes the quantum state of the entire universe without referencing an explicit time variable. In this formalism, the wave function of the cosmos is timeless, encompassing all possible configurations simultaneously. Evolution, in the traditional sense, is absent. Instead, physical reality emerges through correlations among subsystems. One subsystem can act as a clock, providing a reference for the evolution of others. This relational approach reframes the arrow of time as an emergent phenomenon dependent on the structure of correlations rather than an intrinsic property of the universe. Observers perceive sequences of events because they interpret correlations relative to local clocks, creating the sensation of flow within a fundamentally timeless framework. The Page-Wooter's mechanism exemplifies emergent time through entanglement. Consider two quantum systems, one functioning as a clock and the other as a measured system. Their joint state is static globally, yet the clock subsystem provides a parameter that allows the other subsystem to evolve relative to it. Experiments in quantum optics simulate this mechanism, demonstrating that entanglement can generate the appearance of temporal evolution within a globally stationary state. These models suggest that time may arise from information and correlation rather than being a fundamental entity. Although these concepts remain theoretical, they are firmly grounded in established quantum principles and provide a compelling framework for reconciling relativity, quantum mechanics, and human perception of sequential events. Relational time has profound implications for understanding cosmological evolution and black hole physics. Near singularities or in the earliest moments of the universe, classical spacetime may not exist, yet sequences of events can still emerge through correlations between subsystems. The arrow of time arises from the statistical properties of these subsystems, guided by entropy and probabilistic gradients. Black holes, with their extreme curvature and quantum effects, provide a natural laboratory for testing these ideas. Hawking radiation and black hole entropy reveal that quantum processes unfold consistently with an emergent arrow of time, even in environments where classical clocks fail. Observers interpret sequences according to local interactions, maintaining coherent perception, while global coordinates remain timeless. Decoherence plays a critical role in connecting fundamental timelessness to observable sequences. Quantum systems interacting with their environment lose coherent superpositions, producing effectively classical outcomes. This process generates apparent irreversibility, aligning microscopic quantum events with macroscopic thermodynamic behavior. The arrow of time is thus preserved statistically, despite underlying time symmetry in the Schrödinger equation. Conscious experience integrates these outcomes, constructing narratives of past, present, and future. Memory, anticipation, and attention encode sequences that align with operational time, ensuring that perception remains coherent even in a universe where the fundamental equations do not contain an explicit temporal parameter. Experimental research continues to probe emergent time. Quantum simulators, optical systems, and entangled particles are employed to test predictions of the Page-Wooter's mechanism and related frameworks. These experiments reveal that subsystems can behave as if evolving relative to internal clocks, confirming that relational structures can produce temporal experience. While these studies are confined to controlled laboratory conditions, they offer insight into the fundamental nature of time and suggest that our perception of flow emerges from correlations rather than an independent temporal dimension. The arrow of time, consciousness, and operational measures of intervals are intimately linked through these mechanisms, bridging theory and experience. The problem of time also reframes philosophical considerations about causality and determinism. In a timeless quantum universe, sequences exist as correlations rather than absolute progressions. Causal relationships emerge from entangled interactions, yet the fundamental laws remain time-symmetric. Observers interpret these correlations as ordered events, creating the experience of cause preceding effect. Entropy, decoherence, and relational clocks ensure that the arrow of time is locally consistent, preserving coherence and predictability. The interplay between timeless laws and emergent sequences reconciles classical intuition with quantum formalism, demonstrating that time, while not fundamental, is indispensable for perception, cognition, and practical understanding of reality. As this part concludes, the stage is set to explore the final section of the chapter, focusing on theoretical models where time emerges from deeper, timeless principles, the holographic approach, and ongoing debates about the universality of emergent time. The next exploration will examine how these concepts provide a bridge between quantum mechanics, general relativity, and the human experience of temporal flow. offering a cohesive understanding of the nature of time in fundamental physics. Emergent time frameworks extend beyond simple relational models, encompassing ideas that connect quantum mechanics, statistical physics, and cosmology. The thermal time hypothesis, proposed by Rovelli, suggests that time arises from statistical states of systems rather than being fundamental. Within this approach, the flow of time is defined by the evolution of probability distributions over microstates, producing an effective arrow consistent with thermodynamic gradients. Observers perceive sequences because their experiences are correlated with these evolving statistical ensembles. This perspective unites microscopic quantum behavior with macroscopic thermodynamic phenomena, explaining how the arrow of time can emerge in a universe governed by fundamentally time-symmetric laws. The holographic principle offers a complementary view, linking geometry, information, and emergent temporal structure. In this framework, the information contained within a volume of space can be described by degrees of freedom on its boundary. Though originally developed in the context of black holes, the principle extends to broader cosmological and quantum contexts, suggesting that spacetime and time itself may emerge from underlying informational correlations. Adapting these ideas to temporal evolution implies that what we perceive as the passage of time could result from relational changes in information encoded across the universe. While experimental confirmation is limited, these models provide mathematically rigorous and conceptually coherent explanations for how time might arise from a deeper, timeless substrate. Entanglement remains central to the emergence of temporal order. Correlations between subsystems allow sequences to be experienced as coherent events. Even in a globally static quantum state, relative evolution can produce the perception of flow. Experimental simulations demonstrate that when one subsystem functions as a clock, the other evolves predictably relative to it. This relational evolution preserves causality and the arrow of time, ensuring that observers can construct meaningful narratives. Consciousness interprets these sequences, encoding memory, anticipation, and attention, aligning subjective experience with emergent temporal order. The consistency between quantum correlations, thermodynamic gradients, and neural processing establishes a bridge between fundamental physics and perceptual reality. Emergent time also clarifies the relationship between gravity and quantum mechanics. In extreme regions, such as near black holes or in the early universe, conventional clocks lose meaning, yet sequences persist through relational correlations and statistical evolution. Hawking radiation, black hole entropy, and curved spacetime all interact with emergent temporal structures to produce local flow and irreversible processes. Observers embedded within these environments perceive time according to local intervals, while the global quantum state remains timeless. This duality resolves apparent contradictions between the block universe of relativity and the evolving universe of thermodynamics and experience, showing that both descriptions are compatible when understood through the lens of emergence. Neural systems are adapted to interpret emergent time consistently. Brains encode events over discrete intervals, construct coherent narratives, and predict outcomes based on prior experience. Even if fundamental time is absent, operational and relational structures ensure that perception aligns with sequences necessary for cognition and action. Temporal illusions demonstrate flexibility, yet the underlying arrow imposed by entropy, decoherence, and correlation ensures consistency across scales. Consciousness integrates local temporal signals, maintaining a coherent sense of past, present, and future, harmonizing with the statistical and emergent structures of time in the universe. Experience of flow is thus compatible with a fundamentally timeless underlying reality. Cosmological evolution further illustrates the role of emergent time. In the earliest moments after the Big Bang, quantum fluctuations dominated, and spacetime had not yet fully emerged. Sequences of events unfolded through correlations and probabilistic gradients, establishing effective temporal order. Entropy increased, structures formed, and local observers eventually evolved to interpret these sequences. as continuous flow. The arrow of time, memory, and perception all arise from the same fundamental processes that govern the emergence of space-time and matter. This unified perspective reconciles the apparent contradiction between a timeless quantum universe and the experienced passage of time, providing a coherent framework grounded in observation, theory, and experiment. The problem of time, once seen as a paradox, now illuminates the richness of the universe's structure. Time is not merely a background parameter, but a phenomenon emerging from correlations, entropy, quantum mechanics, and statistical evolution. Observers experience flow, causality, and directionality because their consciousness is embedded within these processes. The block universe, relational models, and emergent frameworks coexist, each providing insights into different aspects of temporal reality. Consciousness, perception, and physics are intertwined, demonstrating that the sensation of time is both a product of the universe and a lens through which the universe is understood. Emergent time bridges the gap between timeless laws and lived experience, offering a cohesive, evidence-based understanding of one of nature's most fundamental dimensions. As Chapter 6 concludes, the stage is set for exploring how these concepts extend to macroscopic experience and cosmology. The next chapter will examine the emergence of time from correlations and statistical structures, experimental attempts to simulate these ideas, and how perception aligns with the arrow of time across scales. Understanding emergent time provides a foundation for reconciling physics, consciousness, and the universe's evolution, highlighting the profound interplay between fundamental law and experiential reality. Time as a fundamental entity may not exist at the deepest levels of reality. Instead, physicists and philosophers increasingly view it as an emergent phenomenon arising from relationships between subsystems and statistical patterns. Just as temperature emerges from the collective motion of particles, the passage of time can emerge from correlations among quantum and macroscopic systems. In a globally static quantum state, relative evolution produces sequences of events that observers interpret as temporal flow. The universe may be timeless in principle, yet within it, patterns and correlations give rise to a local and operational sense of before and after. Entropy, decoherence, and relational clocks all contribute to the effective arrow of time, linking microscopic laws to macroscopic experience. Ravelli's thermal time hypothesis formalizes this idea. According to the hypothesis, time can be defined as a parameter along which statistical states evolve. The flow of time is therefore not absolute, but depends on the thermodynamic and probabilistic structure of the system. Observers perceive sequences because their local interactions correlate with these evolving statistical states. Just as temperature only has meaning for a system with many interacting particles, time only emerges in systems with sufficient complexity and correlations. The hypothesis reconciles timeless fundamental laws with the arrow of time, providing a rigorous framework for understanding how local experience of temporal flow arises from the underlying static quantum reality. Entanglement offers a concrete mechanism for emergent temporal experience. When subsystems are entangled, the state of one can serve as a reference for the evolution of the other. This relational evolution allows observers embedded within the system to perceive a consistent sequence of events, effectively generating time from correlations. Experimental work in quantum optics has begun to simulate this mechanism, showing that when one subsystem functions as a clock, the other evolves predictably relative to it. While these experiments are limited in scale, they illustrate that temporal sequences can emerge in controlled, fundamentally timeless systems, supporting the theoretical proposal that time is relational rather than intrinsic. The arrow of time emerges naturally within this framework through statistical mechanics. Local observers interpret sequences of events according to increasing entropy, aligning the perception of past and future with probabilistic gradients. Even in extreme regions of the universe, such as near black holes, or during the early moments after the Big Bang, sequences emerge from correlations and entropic trends. Consciousness perceives these sequences as flowing, constructing memory and anticipation along gradients defined by statistical probabilities. Operational time, defined through motion, decay, and interaction, provides the scaffolding for this perception, ensuring that observers experience a coherent and directed temporal structure, even in a universe that is fundamentally timeless at its deepest level. Relational and emergent time models also clarify the consistency between quantum mechanics and general relativity. Classical notions of time, intertwined with space-time curvature, describe the local rate of events. Quantum mechanics, when considered without a fundamental time parameter, appears timeless globally. Emergent time bridges these perspectives. Local clocks, statistical evolution, and correlations generate sequences that align with perception while remaining consistent with both relativistic and quantum descriptions. Observers navigate a four-dimensional block universe, yet perceive flow and causality because their experience is embedded in the emergent temporal structure. Entropy, decoherence, and correlation ensure that sequences unfold predictably and coherently, linking microscopic law with macroscopic observation. Conscious experience is intimately connected to emergent time. The brain integrates events across milliseconds, seconds, and longer intervals, constructing narratives that align with local operational time. Memory encodes past states. Attention structures, experience, and anticipation predicts future outcomes. Temporal illusions, such as chronostasis or the oddball effect, reveal the flexibility of perception. Yet the arrow of time is preserved statistically, ensuring consistency with physical law. The perception of continuous flow emerges from discrete events, correlations, and neural integration, harmonizing with the fundamental mechanisms that generate time from a deeper, timeless substrate. This convergence illustrates how cognition, physics, and statistical evolution produce a coherent sense of temporal reality. Cosmology provides a broader context for emergent time. In the early universe, quantum fluctuations dominated, and space-time was not fully established. Sequences of events arose from entanglement, correlations, and statistical tendencies, producing an effective arrow of time even before classical clocks existed. As the cosmos expanded, entropy increased, structures formed, and local observers emerged to interpret these sequences as coherent flow. The perception of past, present, and future aligns with probabilistic evolution, demonstrating that emergent time is sufficient to generate the operational experience of temporal order in a universe governed by timeless fundamental laws. Consciousness and physical processes co-evolve, ensuring that observers can navigate, remember, and predict within this emergent temporal framework. Relational evolution, as proposed by Page and Wouters, provides a tangible framework for understanding emergent time. In this mechanism, the universe as a whole exists in a stationary quantum state, yet correlations between subsystems allow one to serve as a clock for the other. Observers embedded within these subsystems experience evolution as a sequence of events relative to the chosen clock. Experiments using entangled photons and quantum optical systems have successfully simulated these dynamics, demonstrating that temporal sequences can be reconstructed from correlations even when the global state is static. These results reinforce the notion that time does not need to be fundamental to produce the operational experience of flow and causality within complex systems. The emergence of temporal order through entanglement also provides a bridge between microscopic and macroscopic phenomena. In the microscopic realm, quantum fluctuations and superpositions dominate, yet correlations allow coherent evolution for observers. At macroscopic scales, thermodynamic gradients and entropy reinforce the arrow of time, producing consistent, and predictable sequences. Consciousness interprets these sequences through neural computation, encoding memory, anticipation, and attention in alignment with local temporal intervals. The integration of quantum correlations, statistical mechanics, and neural processing ensures that temporal perception remains coherent, continuous, and aligned with the emergent arrow, preserving the phenomenology of past, present, and future. Experimental attempts to simulate emergent time offer insight into the operational principles underlying our perception of flow. Quantum systems prepared in entangled states demonstrate that when one subsystem is measured as a reference, the other exhibits evolution consistent with the passage of time. These laboratory experiments confirm that relational structures alone can generate effective sequences, illustrating the theoretical proposal that temporal flow arises from correlations. The results provide empirical support for the concept that time can emerge in systems that are fundamentally timeless, connecting theory, experiment, and perception into a cohesive framework. Observers interpret these sequences as continuous flow, yet at the deepest level, the universe remains static and fully determined. Neural perception complements these physical mechanisms. The brain integrates discrete events over milliseconds, constructing continuous narratives that align with emergent temporal order. Memory encodes previous states, anticipation predicts future outcomes, and attention structures experience to produce coherent perception. Temporal illusions, such as the oddball effect or chronostasis, reveal flexibility in processing, yet the statistical arrow of time ensures consistency across events. This demonstrates that while time may emerge from correlations and entropy, perception produces a continuous experience of flow, seamlessly bridging microscopic quantum dynamics with macroscopic consciousness and lived experience. Entropy plays a central role in anchoring emergent time to observable sequences. In complex systems, the number of accessible microstates increases over time, providing a statistical gradient that aligns with perception of past and future. This gradient ensures that sequences unfold predictably and coherently, allowing observers to construct narratives and anticipate outcomes. Even in regimes where fundamental time is absent, entropy provides the operational basis for the arrow of time, integrating thermodynamic evolution, quantum correlations, and perceptual continuity. Consciousness operates within this gradient, interpreting sequences in a way that preserves causality, coherence, and functional relevance. Cosmological context further reinforces emergent time. In the early universe, quantum fluctuations dominated, and classical spacetime had not yet crystallized. Sequences of events emerged from correlations between subsystems, producing an effective arrow of time without invoking fundamental temporal dimensions. As the universe expanded and entropy increased, the operational arrow became more pronounced, aligning with human perception. Structures formed, processes unfolded, and observers emerged to experience sequences as coherent flow. This perspective reconciles timeless fundamental laws with the lived experience of past, present, and future, demonstrating that emergent time is sufficient to explain the operational and perceptual reality of temporal flow. Relational and emergent time frameworks also shed light on the apparent paradox between the block universe and the dynamic experience of time. While all events exist as coordinates within the four-dimensional manifold, correlations, entanglement, and entropy produce sequences that are operationally meaningful. Conscious observers interpret these sequences as flowing, constructing narratives, and perceiving causality, even though the underlying structure is timeless. Emergent time thus harmonizes physical law with phenomenology, showing that the arrow of time and the sensation of flow are consistent with both quantum mechanics and relativity, providing a unified and evidence-based understanding of temporal experience. Holographic principles provide an additional layer to understanding emergent time. The idea that the information contained within a volume of space can be represented on its boundary implies that space-time, and potentially time itself, emerges from informational correlations. In this framework, the sequences of events experienced by observers arise from the structure of information encoded across the universe. The effective flow of time is generated by changes in the correlations among subsystems, producing the appearance of causality and progression. Though experimental verification remains limited, the mathematical rigor of holographic models supports the concept that temporal experience can arise from deeper, timeless laws without requiring time as a fundamental dimension. Experimental and theoretical studies of emergent time also illuminate the interplay between gravity, quantum mechanics, and perception. In regions of high curvature, such as near black holes or in the early universe, classical clocks lose operational meaning, yet sequences emerge through correlations and entropic gradients. Hawking radiation, black hole thermodynamics, and decoherence all contribute to local temporal order, ensuring that observers perceive flow and causality even in extreme conditions. Consciousness interprets these sequences, encoding memory and anticipation in alignment with operational time. This synthesis demonstrates that emergent time is robust across scales and consistent with both relativistic and quantum descriptions of the universe, providing a coherent bridge between fundamental law and lived experience. Neural systems are finely tuned to detect and integrate emergent sequences. The brain processes events over discrete intervals, constructing coherent narratives that align with operational and entangled correlations. Temporal illusions reveal flexibility in perception, yet statistical and entropic arrows preserve consistency. Memory, attention, and prediction operate within the emergent framework, allowing consciousness to navigate past, present, and future coherently. Even when fundamental time is absent at the microscopic level, the combined effect of correlations, thermodynamics, and neural integration produces a continuous and directed experience of temporal flow. Perception, in this sense, is an emergent phenomenon layered upon the physical mechanisms that generate effective time. Cosmological evolution reinforces the emergence of temporal sequences. In the early universe, quantum fluctuations dominated, and space-time had not yet fully crystallized. Correlations and statistical patterns produced an operational arrow of time, allowing sequences of events to unfold consistently. As the cosmos expanded, entropy increased, structures formed, and observers evolved within these sequences, experiencing temporal flow. The arrow of time, derived from emergent correlations and thermodynamic gradients, ensures that perception, causality, and memory remain coherent. This framework reconciles the fundamentally timeless nature of quantum law with the lived experience of time, providing a unified and evidence-based account of temporal reality across scales. Emergent time also clarifies the coexistence of block universe concepts with dynamic perception. While all events exist as coordinates in four-dimensional spacetime, relational correlations, entropic gradients, and neural processing generate sequences that are operationally meaningful. Observers interpret these sequences as flowing, constructing narratives and perceiving causality even though the underlying framework is static. The sensation of past, present, and future is therefore compatible with a timeless foundation, illustrating how perception, physics, and statistical mechanisms converge. This convergence highlights that temporal flow is not an illusion, but an emergent and real phenomenon arising from the interplay of fundamental laws, correlations, and consciousness. The implications of emergent time extend to fundamental physics, cosmology, and philosophy. Time is no longer required as a primitive concept. Instead, sequences, causality, and experience arise from the relationships between systems. Observers navigate a universe where effective temporal order emerges naturally from correlations, entropy, and statistical evolution. Consciousness interprets these emergent sequences as coherent flow, encoding memory and anticipation that align with operational time. Holographic, relational, and thermal models collectively provide a rigorous framework for understanding how the arrow of time, perception, and causality arise from timeless foundations. The universe, while fundamentally static at its deepest level, produces a rich and directed temporal experience for embedded observers. As Chapter 7 concludes, the framework of emergent time establishes a coherent bridge between microscopic physics, cosmology, and human perception. Time is revealed as a phenomenon that arises from correlations, entanglement, statistical gradients, and neural interpretation. Observers experience sequences, flow, and causality, yet at the deepest level, the universe remains timeless. This understanding sets the stage for exploring the fate of time in the cosmos, the potential end of change, and how temporal perception continues to arise, even as entropy and expansion shape the ultimate trajectory of the universe. The next chapter will examine these questions, connecting emergent time with cosmology and the long-term evolution of temporal experience. The story of time stretches not only through the past but into the distant future, where the universe itself becomes a witness to its own transformation. As cosmology reveals, the expansion of space continues relentlessly. Since the discovery of redshifts by Edwin Hubble in the early 20th century, scientists have known that galaxies are moving away from one another, carried by the stretching of spacetime. The farther a galaxy lies, the faster it recedes. Observations of supernovae and the cosmic microwave background, measured by missions such as Planck and WMAP, confirm that this expansion is accelerating, driven by a mysterious component known as dark energy. This expansion reshapes the future of time itself, defining how events will unfold, slow, and eventually cease. If the universe continues to expand forever, entropy will increase toward a state of maximum disorder. Stars will exhaust their fuel, galaxies will fade, and black holes will slowly evaporate through Hawking radiation. Over unimaginable stretches of time, trillions upon trillions of years, the cosmos will grow darker and colder. Matter will decay, and the few remaining particles will drift apart through an ever-thinning sea of energy. In such a state, no meaningful change can occur. When energy gradients vanish and processes reach equilibrium, clocks lose their meaning because there are no longer events to measure. Time does not end in a sudden collapse. It fades as change disappears. The physical definition of time, the measure of change, ceases to apply when nothing changes. This cosmic fate is often described as the heat death of the universe. It is not an explosion or a freeze, but a quiet dissolution of structure. Entropy approaches its maximum possible value, and the distinctions between past and future lose operational meaning. Physics does not predict that time itself stops, but rather that the universe becomes timeless in practice. Without interactions or thermodynamic differences, there is no before and after that can be distinguished. In this deep future, time remains as a coordinate in space-time, but not as a living experience. The arrow of time, once defined by increasing entropy, will fade into silence. Other scenarios have been proposed: the Big Rip, where expansion accelerates until galaxies, stars, and even atoms are torn apart, or the Big Crunch, where expansion reverses into collapse. Yet current observations suggest the universe will continue expanding indefinitely. Dark energy, with its constant density, ensures that acceleration will persist. The galaxies beyond our local cluster will drift beyond our horizon, their light redshifted until it disappears. For any observer billions of years from now, the sky will grow empty, the universe dimming into isolation. Time, for such observers, will continue to exist mathematically, but not experientially. Even within this cosmic stillness, the emergence and fading of time remind us that temporality is tied to change, interaction, and observation. The universe began with extreme order, a low entropy state near the Big Bang, and has evolved toward increasing complexity and eventual uniformity. Time's arrow points from simplicity to dispersion, from energy to equilibrium. When that process completes, time's function ends naturally. The universe becomes a static geometry, a block of existence where all events from the first star to the last photon are embedded eternally. Time as flow disappears, but time as structure remains. The future of time, therefore, is not an end, but a transformation from dynamic progression to silent geometry. The universe defines time through motion, decay, and change, but consciousness defines it through experience. Inside the human brain, billions of neurons fire in intricate synchrony, constructing the illusion of continuity. Neuroscience reveals that perception is not instantaneous, but assembled across brief windows of integration, fractions of a second, that the mind stitches together into a seamless flow. Experiments by scientists such as David Eagleman and Dean Buonamano demonstrate that the brain operates like a prediction engine, aligning sensory input, memory, and anticipation into coherent temporal narratives. We do not perceive events as they occur, but as reconstructions, delayed slightly, yet experienced as immediate. This temporal integration is essential for survival. If perception were truly instantaneous, reality would appear fragmented and chaotic. The brain averages information across short intervals, typically a few hundred milliseconds, to create stability. This process produces the sensation of now a moving window of awareness that feels like the present. Cognitive scientists describe this as the brain's temporal binding function, where discrete signals are combined into continuous perception. The experience of flow, therefore, is a construction, emerging from computation and memory, rather than direct measurement of external time. Emotion and attention shape this inner clock. Fear or excitement accelerate the brain's processing, making moments feel elongated, while routine or boredom compress experience, making hours seem to vanish. These distortions demonstrate that subjective time is plastic, governed by neural states rather than by physical clocks. Memory plays a central role as well. The richness of encoded detail affects the perceived duration of an event. New experiences create more memory traces, making time feel slower in retrospect, while repetition creates fewer, making time seem to speed up. Thus, the arrow of psychological time depends not on entropy but on attention and memory. Within the brain, specialized structures coordinate temporal functions. The basal ganglia and cerebellum manage interval timing and motor coordination, while the prefrontal cortex handles sequencing and prediction. Neural oscillations synchronize these processes, creating rhythmic patterns that maintain temporal coherence across sensory systems. Through these oscillations, the brain generates its own internal clock, calibrated not in seconds, but in cycles of activity. This internal rhythm allows humans to anticipate motion, recognize patterns, and plan behavior. Consciousness, therefore, is a temporal computation, grounded in neural dynamics that mirror the statistical flow of the physical world. Yet despite the vividness of temporal experience, no evidence suggests that consciousness alters physical time. The flow we feel is not a property of spacetime, but a feature of neural computation. Physics provides the coordinates. The brain provides the narrative. The psychological arrow of time aligns with the thermodynamic arrow because memory formation requires increasing entropy, the irreversible recording of information in matter. The brain's encoding of experience consumes energy and increases entropy locally, binding subjective time to the universal arrow. Consciousness does not cause time to flow. It rides upon the same statistical currents that define all change in the universe. Through this synthesis, perception becomes a bridge between geometry and experience. The block universe may contain every event, Yet the brain experiences them sequentially, one constructed moment at a time. The sense of moving forward emerges from how consciousness organizes data, interprets memory, and predicts the next input. In this way, humans carry within them a time machine, not one that travels through space-time, but one that continually reconstructs it. The mind creates motion from stillness, flow from structure, and story from silence. Time, within the brain, is not measured, but imagined, and yet it feels as real as the ticking of any clock. When physics, cosmology, and neuroscience are brought together, a coherent picture of time begins to emerge. The universe itself may not flow. It simply exists as a four-dimensional geometry, where all events, from the birth of galaxies to the blink of an eye, are woven into a single space-time fabric. The block universe interpretation of relativity shows that past, present, and future coexist as coordinates, each equally real. Yet consciousness experiences these coordinates as sequences, translating structure into story. This duality between timeless geometry and temporal experience defines the deepest nature of reality. In this framework, causality persists even without fundamental flow. Sequences of events still follow laws, and correlations between cause and effect remain consistent within space-time. Entropy provides the direction that distinguishes before from after, ensuring that processes are oriented and memory is possible. Consciousness interprets these correlations, generating a perception of progression. Thus, the experience of flow arises not from the universe itself, but from the relational structure between observers and events. Time, in this sense, is both a coordinate of the cosmos and a construction of the mind. Philosophy joins science in confronting what this means for existence. If every moment already exists, then the present is simply the perspective from which we view the manifold. The future is not being created. It is being revealed along the path of observation. Free will remains compatible with this view, not as the power to alter space-time, but as the capacity to navigate it, to experience and interpret different coordinates as choices unfold. Meaning, memory, and identity persist, not because time flows, but because consciousness constructs continuity from stillness. Ultimately, time is both fundamental and emergent. It is the coordinate that orders events and the experience that gives them context. Physics describes it geometrically, while neuroscience explains it phenomenologically. Together, they reveal that the flow of time is an illusion that feels real because it must. Without the arrow of experience, there would be no memory, no anticipation, and no consciousness to perceive existence at all. The universe may be silent and eternal, but within us, time is alive, unfolding, remembering, and dreaming. Perhaps the universe never waits, only we do, tracing the same eternal structure again and again, forever moving through the unmoving whole. In the end, perhaps the greatest revelation is not that time bends, flows, or loops, but that it is us who move through its vast coordinate, not as passengers, but as interpreters of existence. Every heartbeat, every memory, every flicker of awareness is a point along the continuum, stitched together by consciousness into the illusion of flow. The universe itself does not rush forward. It simply is an eternal tapestry of all events already written in the language of space-time. Yet within that stillness, life burns brightly, giving motion to the unmoving, meaning to the infinite. We are the storytellers of the cosmos, translating timelessness into experience, transforming geometry into destiny. And perhaps, in recognizing this, we do not escape time, we become it.